we need to remember this, we will be needing it further. Yt minus expected value of yt is equal to 1 upon 1 minus beta ut. Now we want to see the covariance between yt and ut. So we write it in the formula for covariance. Like I say, if you want to find the covariance of x and y, you can write is expected value of x minus expected value of x, this is 1, and then next time you have y minus expected value of y, and this is the second term. Similarly, in place of now x, you have u. So we can write the covariance of yt ut as expected value bracket open yt minus expected value of yt bracket closed bracket open yt minus expected value of ut bracket closed. Now, this I am writing in this format. Expected value of ut is equal to 0 and yt minus expected value of yt we have just now seen is equal to 1 upon 1 minus beta ut. We have just now derived in our in our this slide here only we have just now derived it. Now, so this yt minus expected value of yt, we write it as 1 minus beta ut. This expected value of ut is cancelled, it becomes 0. So what is left here is only ut. So now I can write, now there is ut over here and ut over here. So I write it as expected value of 1 divided by 1 minus beta ut square. Now ut square we can write it as sigma square. And so this is sigma square and this is 1 upon 1 minus beta. So we can say that the covariance of yt and ut is not equal to 0. Now let us do another scheme of equations. Now let us try to apply OLS. What we do? We try to apply OLS. This is my system of equations. Say Ct is equal to alpha beta yt plus xt. Normally when we had y is equal to alpha plus beta xt plus ut, what we used to write? We used to write it as beta is equal to summation x minus x bar y minus y bar divided by summation x minus x bar square. So here since it is we have c and y, so what we write? We write it in this format, that is summation ct minus c bar multiplied by yt minus y bar divided by summation yt minus y bar multiplied by yt minus y bar, or the denominator can be said yt minus y bar square. This is in the deviation format. This capital C t minus c bar can be written as a small c, yt minus y bar can be written as a small y, and this can be written as small y. Small y is nothing but y minus y bar, and since there are two terms, so we do the square of it. So this is your formula for beta hat over here. Now we come to the realm of second order moments. Now what we write? We write it as mcy is equal to 1 upon n summation ct minus c bar yt minus y bar. See, and if it is just like myy, here there are two y's only, so this is defined as 1 by n summation yt minus y bar multiplied by yt minus y bar. So here similarly we have mci, here we have small c is written like this, small I is written like this, and here it is ii. So small I, and this is also it minus I bar, it minus bar. Now see, here they represent the sample covariance and sample variance between different variables in the system. The notation Ct, Yt, It represent the sample mean of the variables. What are those sample means? C bar, Y bar, I bar. Now what is variance? That the second order moment of a single random variable represent the dispersion of spread of values from the mean. And covariance, where we have two terms C and Y, the second order moment involving two random variables measuring how much those two variables change together. So this mcy and myy are second order moments representing the covariance and variance of variables ct and yt respectively, and mci and mii are the second order moments representing the covariance and variance of variables ct and it respectively. Now your this earlier equation, what you had, one second. So bt was equal to summation cy and yt. Now what we do, we simply bt is equal to, we can write it as, we multiply it by the denominator and the numerator both by 1 by n. So we can say 1 by n summation ct minus c bar yt minus y bar, and in the denominator is 1 by n summation yt minus y bar and multiplied by yt minus y bar. Now you reduced from the reduced form. If you remember, this was my equation we have derived by reduce in the reduced form for yt. Yt is equal to alpha 1 minus beta plus 1 upon 1 minus beta it plus 1 upon 1 minus beta ut. If I want to write in the mean format, so here in place of yt I take I bar, and in place of ut I. So now yt minus y bar, we can write it as this is the term for yt. These are the three terms for yt: alpha 1 minus beta plus 1 upon 1 minus beta plus 1 upon 1 minus beta ut. And these three terms are for y bar, that is minus, all are coming in the minus because here we have the sign minus. Minus alpha 1 minus beta minus 1 minus beta I bar minus 1 minus beta u bar. This term and this term, they can be cancelled out. One is they are the similar terms with different signs. Now what we are, and we can then combine these two, that is 1 upon 1 minus beta it minus 1 upon 1 minus beta I bar. So taking 1 upon 1 minus beta common, we can write in a bracket it minus I bar. Similarly, we will be taking these two terms common, that is 1 upon 1 minus beta ut minus u bar. We have taken ut from here and u bar and 1 upon 1 minus beta as common, so we get the second term. We do the same thing for ct. These are the three terms representing ct, that is alpha 1 minus beta plus beta 1 minus beta it plus 1 upon 1 minus beta ut, and this c bar, these are the three terms representing c bar. So we write it in the minus with a minus sign, minus alpha 1 minus beta minus beta 1 minus beta it minus 1 upon 1 minus beta ut. So two terms, this term and this term, alpha 1 minus beta, they are coming two times, one and once with a positive sign and the second time with a negative sign. So what we can do, we cancel these two, then we combine it, and this is, excuse me, this is I bar and this one is u bar. Please note this correction. So now what we can do, this it and I bar, we combine it minus I bar multiplied by beta 1 minus beta, and ut and u bar, these two terms we combine, and we can write taking 1 upon 1 minus beta common as 1 divided by 1 minus beta ut minus u bar. So now what we had ct minus c bar and yt minus y bar. We have just in the previous slide we have derived, this is for yt minus y bar, this is for ct minus c bar, and because what we are basically trying to do is, we are trying to write down the equations for this, the model, the terms for these equations, this equation. So we can write it in this format. We have, this is nothing but ct minus c bar, and this is nothing but yt minus y bar. Now we open the bracket, we cross multiply first beta 1 minus beta with this, so we can get beta 1 minus beta square and it minus I bar square. Then we write, we multiply this term with the second term, that is beta 1, here also beta 1 minus beta, and here it is beta 1 minus beta. So 1 minus beta 1 minus beta square multiplied by it minus 1 multiplied by ut minus it minus I bar multiplied by ut minus u bar. Next time we multiply this with this, so it is in the down it becomes, now down it becomes 1 upon 1 minus beta square it 1 minus beta square it minus I bar multiplied by ut minus u bar, and next time it becomes 1 upon 1 minus beta square ut minus u bar. I think it is 1 minus 1 1 upon 1 minus beta ut minus u bar, and this is also, so there is a square term over there, and it is it minus I bar ut minus u bar, and yeah, it is correct. Only thing is beta will be coming over here, this beta, because it has a beta also over there. Let us cross check it whether beta is there in the yt minus y bar equation is correct or not. So if you see yt minus y bar equation, no, there is no beta, excuse me, since there is no beta, this is it minus I bar, we have it is it minus I bar, so this was correct. There was a mistake over here, that is I. This is 1, excuse me, this is 1 upon 1 minus beta. So as it is, we take, and in the in the denominator this square is there. So now we have this equation. Once we get this equation, now we multiply both the right hand side, the left hand side and the right hand side, both by 1 upon n, because in our initial thing from where we have started, there is 1 upon n. So now we write this equation as 1 upon n summation ct minus c bar y multiplied by yt minus y bar. We write this whole term. Everywhere I am incorporating in the previous equations derived 1 by n. In the previous equation which we have derived, we just incorporate 1 upon n in all the terms. Now this is it minus I bar as we have assumed before in the sense what I am referring to here. So we write it in that same term, and we say that this is nothing but, since it is it minus I bar, we write it, this is m11. Here it is it minus I bar ut minus u bar, so we write it as miu. This one is I and u. This is it, there is a correction over here, this is it minus I bar. So m1u, and this one is u and u, so muu. So mcy, this is what this is nothing but this term is nothing but your mcy. Mcy is equal to this term, that is beta 1 minus beta m11 plus 1 upon 1 minus beta square. Now here miu and miu is common, so we are taking it as common, 1 upon 1 minus beta square miu plus, here it was beta miu, because this beta is over here and we have taken out common only 1 upon 1 minus beta square. So beta miu plus miu, and the last term, that is 1 upon 1 minus beta square muu. So this is my final equation as such over here. Similarly, we will write it for myy. Myy we have yt minus y bar and yt minus y bar, and we have seen it, yt minus y bar was equal to 1 upon 1 minus beta it minus I bar plus 1 upon 1 minus beta ut minus u bar. So now since there is a square, so the same term what you are doing, you are writing a square over here. Now square means you can write it in the format of a plus b square. So this term is a, so I write a square, so 1 upon 1 minus b, that becomes a square, and it minus I bar square. Now the b term is 1 upon 1 minus b square ut minus u bar square plus 2a is this term. And now there is one step we have consumed, there is a is 1 upon b and 1 upon b we are combining, so we are writing it 1 upon 1 minus b square, and it minus it is it minus I bar, it is it minus I bar, it is ut minus u bar. Please note these corrections. So 1 upon 1 minus b square it minus I bar ut minus, again another correction, it is minus sign should be there, ut minus u bar. Again, like in the previous case, we multiply both the sides, the right hand side and the left hand side of the equation, by 1 upon n. So 1 upon n is incorporated in all the terms. Here there is y bar. So 1 upon is incorporated in all the terms. Now, again, as we have seen how we write m11. So this, because it is it minus I bar, we write it as m11. This one is ut minus u bar, and there is ut minus uh, it is ut minus u bar, and there is also a square of it. I have missed the square sign over here. Please note this correction, the square sign is missing. So we write it as muu, and here the last term, it is 2 1 upon, this term is keeping 2 upon 1 upon beta, and this is iu. So it becomes I1 iu. So myy can be written as 1 upon 1 minus beta square mii plus 1 upon 1 minus beta square muu plus 1 upon 1 minus beta square miu. Now, what is the formula for beta? Beta is equal to mcy by myy. This was what this is what we started with, 1 upon n summation ct minus c bar yt minus y bar divided by 1 upon n summation yt minus y bar square. Now, we have seen what is the value. Just now we have derived the value for this mcy, or for this. Now I can further taking all the 1 upon beta is here also, here also, here also, and here also. So we take common over here. mii we write over here, but beta is missing. Beta should also be there, and miu, beta is here, so I write it over here. miu I write it over here. muu I write it over here. Similarly, for myy, it is nothing but 1 upon n summation yt minus y bar whole square. So we have just now derived the equation for it. It is now. Again, I take common 1 upon 1 minus beta square, I take common. So here it is coming 1 upon 1 minus beta square. I am writing outside in the bracket m11 plus m22 plus 2 miu. Now, the denominator term is this. I take it down. This is the denominator term, and this one is the numerator term. So here, in outside the bracket, it is 1 minus b whole square, and in the denominator is also 1 divided by 1 minus b whole square. So this and this is cancelling. So you are left with beta m11 plus m1iu plus miu plus muu. It is not beta 11, it is basically beta ii. Beta mii plus beta miu plus beta plus miu plus muu divided by m11 plus 2miu plus muu. Since it was a very long equation, I just summarize it quickly. This, we started with this thing, and ultimately we ended up with this thing. For CT, we got this equation. For the denominator, it was this equation, and then we finally divide and we get this value of beta. Now, see, I is an exogenous variable, so there will be no correlation between I, that is your investment, and the disturbance term. And when n tends to infinity, that is the sample size becomes huge and large, miu is equal to 0. So 0, 0, 0. You are left with beta m11, you are left with beta m11 m plus muu divided by mii, sorry, not 11, ii plus muu. Muu is nothing but your variance. Error multiplied by error. This is your variance. Now, so we can write, we take the probability limit. If we take the probability limit of beta hat is equal to, we can write it as the same thing, and in place of muu we are writing s square, in place of muu you are writing s square. So probability limit of beta is equal to beta mii plus s square divided by mii plus s square. Now, what our basic purpose was to show that the estimator is biased or not. So what we do in order to show this biasness, we add and also minus by the same term beta. So in the right hand side of the equation, we add a beta and we minus a beta. So basically it will not put any effect because we are adding by the same term and deducting by the same term. Now this beta which was over here in the positive sign, we take it over here. So we get plim beta hat, probability limit of beta hat minus beta is equal to, what is left is beta mii plus s square divided by mii s square, mii, sorry, there is a plus sign missing over here, minus beta like over here. Now, since it is in the denominator and there is 1 over here, we apply this simple algebraic process. So, what we get, beta mii plus s square minus, we multiply this with this, beta m multiplied by mii plus s square, and now we can write for the entire term, we can write in the denominator mii plus s square. So plim beta hat minus beta, we can write, we can now the next time we open the bracket and accordingly adjust the sign. So it becomes beta mii plus s square minus beta mii minus beta s square divided by, in the denominator it is mii plus s square. So now what we can say, plim beta minus beta hat minus beta is nothing but equal to s square. This and this is cancelled because they are the similar terms with opposite signs. So we can write it is as s square minus beta s square divided by mii plus s square. And s square is a constant, beta 1 is a term, so this is not equal to 0. So if it was a consistent estimator, plim beta hat minus beta should have been equal to 0. Probability limit of beta is equal, beta hat is equal to beta for a consistent estimator. But here the estimator beta hat is not consistent. Here the estimator beta hat is rather biased and inconsistent. And this is what we refer to as simultaneous bias. So we had a discussion on simultaneous equation. What is a simultaneous equation? Why we need to study simultaneous equation? What happens when there is dependence in the variables and and we have seen that we don't use independent and dependent, rather we use exogenous and endogenous. Then we have seen what is a structural model, what is a reduced form model, and also final form model. Then we prove that if you are applying OLS, your estimator, that is your beta hat, is unbiased, and it's not our requirement, that is the best linear unbiased estimator blue. With this I end today's this lecture. Thank you very much.